So, value of SML. It's adoptable and intuitive. The whole system was designed to make it as simple as possible for any user. So it doesn't matter whether you come from an engineering background or you're a data scientist, even down to someone like me, where that's not necessarily your primary education. You can go in here, get into the system, and start utilizing it with minimal guidance. And another key component is it's collaborative. The system was designed to make sure that whether you're running the solution by yourself or if you're in a team of different individuals, you can group together on different experiments, different data sets, even the overall presentation of your findings to make sure that everyone is coming together and is on the same page. And then some big key components for our clientele is the fact that it's quick. SML can usually run through a modeling and prediction process 10 to 100 times faster than the standard methods. It's very efficient and it's very accurate and certainly very powerful. The background of the algorithms and the back end of how SML was designed is it's really meant to take as complex of problems and be able to get you the predictive analytics that you're looking for. And then the one key thing that everyone loves is it's cost effective. We're not your enterprise level solution that's going to cost you $1 million a year. This is something that is affordable at any level to make sure that you can be really strategic and have the leg up against your competition in the marketplace. So as we look at this, we're going to look at 3 use cases today. Those are wind power forecasting, solar power generation, and water pump failure. So with each of those respectively, first, we're going to identify the relationship between wind power generation and the respective variables that go into that. For solar power, we'll look at the necessary inputs that are meant to achieve a specified target energy generation. And then lastly, this is our Amphos 21 use case. This is a current client of ours that utilized this use case in actually winning a competition where they took first place. And what they meant to do was managing false positive rates and predicting which water pumps would require maintenance at any specific interval. So as we jump into that, let's look at use case number 1, power generation from measured parameters. If we look at what the problem was, is we needed to accurately model the power generation of a turbine based upon specific parameters that were observed from weather records. And what we were able to determine is as we ran the modeling for this and looked through the entire process, and what that resulted in was accurate predictive models where we were easily able to obtain this information by applying smart, built-in, and the automated capabilities of SML, which we'll discuss in our demo today. Also, we were able to determine that the most relevant variable to our predictive model, our experiment for wind power generation, was overall wind speed. And as you can see here, we've got a lot of graphs that were meant to support that. Then if we look at solar power generation, this is another area where we found that there were a lot of great applications for SML, SpeedWise machine learning. And what we were looking to accomplish here was to build a model that can automatically identify the relationship between a target energy generation and, once again, a set of specific inputs or variables. And from that, our findings were very similar from the solar power generation. We were able to generate 2 different models in this case that were actually able to forecast the energy generation of the entire solar plant based upon those specified variables. And lastly, use case number 3, water pump failure. This is Amphos 21's experiment and is now published and is just such an awesome use of SpeedWise machine learning. What they were looking to accomplish was to find false positive rates in order to dispatch specific maintenance crews to those pumps when needed. And as you can see here in the graph, we were able to look at some of those variables, so faulty versus functional, and how accurate those readings, those measurements were, so that we didn't waste time and energy going into pumps and getting false readings, and it turns out that that pump was working. So as we look at this, what did we want to accomplish? We needed to find what those false positive rates would be so that we could dispatch 10% of their dispatch our maintenance crews to 10% of those pumps as our resources allowed. And this resulted in observing 55,400 different pumps and finding that 32,259 of those were functional at different intervals. And from that, we were able to determine with specific accuracy, so 90% accuracy in the training set, 82% accuracy in the test set, which pumps would require that maintenance and where we could expense those resources to go and maintain those pumps at different intervals. So it just ultimately ended up being a really successful experiment and can really set the stage for changes in these different areas where those pumps are imperative to the success of the region. So as you can see here, AMPHOS 21 is an international scientific consulting firm. So these guys know what they're talking about. And by using SML to build that predictive model, they were able to forecast the quality of water leached from mining waste deposits. They were able to determine the quality of water in natural lakes that are affected by deep geological storage systems for nuclear waste. And they were also able to emulate numerical simulators of chemical reaction processes in water just with immense speed and accuracy. And then the challenge that this was proposed by was the Smart Catalonia Challenge. And with that, once again, we're excited to report that they were able to take first prize out of 40 different competitors utilizing our SpeedWise machine learning software. So a huge congratulations to AMPHOS 21 and their success there. Now, as we look at this, what does that mean for you and your organizations in the renewable space, in the utility space, and how can we apply this in your different organizations? So as we look at this, what is SML? It's that machine learning software to where, once again, anyone from any background and knowledge set can utilize this to generate predictive models. And that all starts with data. So for today's demonstration, we're going to use a simple use case, and that is the solar power generation that we had discussed earlier. And so I'm going to show you a quick data set because, frankly, that's where it all starts. So SML is meant to intake any amount of data that you have to generate these machine learning models. And as you can see here, I've got your basic CSV or Excel file showing all of the different variables that play into this model. So what we're going to do with this data set here is we're going to just plug it right into SML and utilize this to create a predictive model. So if we change over here, let's take a look at SML. So now that we've got our data set, what you're seeing now is the landing page for SML. So welcome. This is the software. This is where you will go as a user to begin your experiments and upload your data sets. And that's really where, as I said, it all starts. Let's go ahead and upload a data set. And so as you can see here, this is where a lot of that collaboration starts. You've got your data sets that you may have internally that you're working on, and then you can share those across the board with your peers so that if it's a joint experiment that you're working on together and training this model, you can do so together. So let's create a new data set. And let's name this solar power and put that in the system. Now, once we do so, we can come in and once again drag and drop or browse and click for that specific data set. So I'm going to go ahead and upload our Plant 2 weather sensor data that we'll use for today's experiment. And I'm going to create a workspace. Now, once again, coming back to collaboration, we did so with the data set. Now we can do so with the workspace so that we can publish to the team or so that we can share these experiments across the board so that everyone's on the same page. So today we're going to name this workspace AWS Solar Power. And there we go. It's as simple as that. Now we've got a workspace created to where we can just hit the ground running and begin experimenting. Okay, so now that we've created that workspace, as you can see here, the system will now navigate us to our different workspaces, where we can choose where we want to begin experiments with specific data sets. And yet again, as I mentioned, this is a common theme. It's meant to be collaborative. So you'll have your shared workspaces where your peers can go ahead and publish their experiments, and you can see and review those, or you have your internal experiments that at some point afterward, you can go ahead and share at any time. So for today, let's go ahead and just start a new experiment. And let's call this solar power generation. And we're going to go ahead and place this in the AWS solar power workspace and generate an experiment right from the get-go. Now this is where it gets fun, is if you've got multiple data sets, you can go ahead and choose from any of those, because the system will populate those. As we've just got one today, it makes it nice and easy. And then we've got to set the parameters for the problem that we're looking to solve for. So in this case, we found that what we wanted to solve for was the DC power generation based upon these different inputs or variables. And the very first thing that you'll notice, and this will also become a common theme in today's demonstration, is that the system is guiding you along at every different stage. And so we'll notice that in this case, the system has told us that regression modeling is probably going to be the best fit for what we're looking for DC power generation. And it will even guide you with these little quick tips along the way. So you'll see those as we go along. But that's it. Let's move on to pre-processing. Now, pre-processing, if you know or maybe you don't know, tends to, in the machine learning space, be one of the most complicated stages of the modeling process, because you've got to clean up your data. You've got to make sure that you've got the right inputs for the predictive model that you're looking for. And what the system does is it provides a lot of automation here. Now, before we look at that automation, we also have some great ways of visualizing the data that we're looking at. So we can come in and we've got things like distribution plot, to where we can select all of those different variables and get violin distribution plot outputs. And we can see if there are any outliers at any of these different inputs. Apart from that, we've got a nice feature correlation matrix where once again, we can take any different variables that we're looking at and we can see how they plot against one another in terms of their correlation. So in this case, let's use a Pearson correlation plot. And let's go ahead and use a hot color scale. So within here, we can see how those different inputs correlate one with another. And this may help us in determining what inputs are duplicated or what inputs we could get rid of, because we've got other variables that we can base our model off of. And then lastly, we've got this feature pairwise plot, to where we can match up different pairs of features, one with another, to see how they might affect the overall outcome. So in this case, we could look at ambient temperature versus the DC power. And we've got a nice pairwise plot there. Now, once we've looked at that, that'll help us once again identify the different features that maybe we need to leave in, maybe we need to remove from our pre-processing. Now, here's where the fun really comes in at the pre-processing stage, because the system is really, like we mentioned earlier, going to automate as much as possible for this. So if we need to set a train test split where we set aside a specific amount of data for training and utilize a test grouping to verify accuracy on that, the system will already set that apart. Now, if you are a data scientist or a machine learning engineer, of course, you can come in here and do this manually and set different parameters for what you like. Another huge area is imputing missing data. A lot of times we'll get data sets where a column may have 50, 60, or even higher percentage of missing data. And if we're not going to remove that, and it's going to be pertinent to how our predictive model goes, we need to put that information in there. So the system can actually go in and fill in those different spaces, whether that's through simple mean mode or through its own little machine learning algorithm to fill in those blanks. And lastly, categorical encoding. So taking any text properties within these data fields and converting it into a numeric value that can be read in the model. Now, before we get there, just because we're a little bit ahead of the curve with this particular project, I'm going to go ahead and do a couple quick things. So this is where you can come in and really treat for anything that you'd like on a manual level. So in this case, since we've got some date and time variables in here, I just want to clean those up real quick. So as you can see, nice, quick, and easy cleaning up those date variables, those time variables. And then from here, we've also, ahead of time, identified a few areas that we want to remove. So I'm just going to go ahead and remove a few of these features and get it to where we want it to be. So we want to keep ambient temperature, date frac year, irradiation, temperature, and time frac day. So now the system will completely remove those other features that we don't feel are going to be pertinent to our model. And now we can turn on autopilot. This is where the system, where SML is going to go ahead and start cleaning up our model in pre-processing, getting it ready to be trained. Now you'll notice here that once I've done that autopilot, it's going to show me that whole set of different operations that I conducted. That way, if you're doing this with a peer, if you're sharing this workspace or experiment, your peers can see what was done to prepare this data for training. So that's it. That's how simple pre-processing is. Now, to put that into context, pre-processing for a large problem can sometimes, using standard practices, take days, weeks, months to clean up and get that data ready for training. And as we can see here, albeit a simple problem that we're solving for, we were able to do it in a matter of minutes. And so now we're ready to start training. Now, the great part about this is SML does not require any sort of coding. So the algorithms and everything that we're doing here for pre-processing is set within the system. So once again, coming back to the fact that this is meant for everyone. You don't have to be a data scientist or a machine learning engineer to utilize this system. And if you are, it just makes it all the more easy for you to follow these steps on your model training process. So let's go ahead and use a nice regression model to get this going. Now, SML is really awesome in the fact that you can run multiple different models at the same time. And you can turn it on, once again, to autopilot. So that if you don't want to necessarily go in and set specific parameters, you can just start generating models right from the get-go. And the best part is you can see how those jobs are running in real time. So that as it starts to run those, you can see how close or how accurate your readings are as they progress. Now, for the sake of today, we're not going to let it run the full level, but as you can see here, it still doesn't take much time to run these models. But once we see that it's kind of flat-lined and it's accurate, if we'd like to, we can actually stop that job if we've got the readings that we're looking for. And so we'll do the same for this one over here. And that's it. We've run our models. And now we can really start to look at what the end result is for each of these different items. Okay, so now that we've stopped both of those models from running, let's go ahead and start to finalize these models. Now, the best part is we don't have to just use one singular model. We can use multiple at once. And we can actually ensemble those and piece them together. So in this case, we could do a mean, a lasso, or a ridge. And basically, this just combines those different models together to get us an end result for reporting and looking at those predictions going forward. So in this case, we're just going to use a nice simple ensemble, the mean ensemble, to bring those two data sets, those two models together. And once we've done so, we're ready to see final results. So let's move on to the playground. Now, the playground is a great way of interpreting what all of this data means from our models. And as you can see here, there's a bunch of different features that you can play around with. Now, first and foremost, let's see how the model actually ran. we can see that on all bases, that model was very accurate and ran very well. And obviously, dependent on the problem, this may look a little bit different. For once again, today's simple plot, this went extremely well. We got great results. And from here, we've got a bunch of different other features that will help us understand what played into those overall results. So two of which, the feature contribution and partial dependence, will help us understand what each of those variables played into the overall outcome of this model. So as we can see here with the feature contribution analysis, we found that the module temperature played into the result of this model the most. And if we come back here and look at the partial dependence, we can once again look at each of those different variables and see how they played out against the DC power output. And this is extremely important because this will help you identify key components as you're reporting this out to your team. Now, a true versus prediction, what this enables us to do is really diagnose how accurate the readings were, both in our training set and our test set. So the more closely aligned to that 45-degree angle line that we're looking at here, the more accuracy we had in our findings. That way, if we see these different results popping up outside of the 20% error line, we may need to do some diagnostics on our modeling and figure out where things are going wrong. But ultimately speaking, as we can see here, this ended up being a very accurate model, both in the training and testing phase. And as we come back here to the playground, hopefully not to overload the group here, but there are just so many different things that you can take away from this and easily illustrate to the remainder of your team or even to an executive group if a really important decision is needing to be made. So in this particular case, as we're looking at solar power generation, if we need to make quick changes with any of these different variables or placements or whatever the case may be, we can do so. And then we can also quantify the uncertainty of our model. This is a key determination of running these different predictions, especially for the team and for the executive team if we need to make any course corrections. Because what this does is this actually shows us the risk that if we were to make a specific prediction, how accurate is that prediction going to be? So we can say that when we make a prediction here along this line, we have a high confidence level that there's going to be minimal risk of us being wrong with that prediction. So as we go back here, there are just a few last items that I think are really key. Now, one, I'm going to get started really quick. You can actually generate a full-scale report within SML for presenting these findings. So I'm going to let that run for a minute as the system's going to go ahead and generate that for me. But I can actually come in and make a prediction firsthand. So whether that's uploading a file or in this case, we might as well utilize the information that we've got stored in the system from our model to make a specific prediction. So this will generate that prediction for us right here, once again, so that we can report and with that confidence level, show how accurate we're going to be in that prediction. So pretty neat. As we come back here, the last three things that are really important are first going to be the generating the API key. So we can actually create a bridge to things like MATLAB or to Python or JavaScript, these findings to call back to this information at any time. We can also review this experiment. This has been extremely helpful for me, that as our data scientists run some of these models, I can go in and see what they've done to get that result so that either I can mimic it or I can go in and run it for an experiment with slight different alterations in the pre-processing steps, whatever you need to do there, but it gives you a guideline. And certainly you can publish your experiments. We want to make sure, once again, tying back to collaboration, that everyone is on the same page on these results. And lastly, bringing that back to the report. Seeing what those results inevitably ended up being, you're typically going to have to present this to your team or maybe the executive group. And this, once again, will generate all of that for you. so that you can go in and easily illustrate your findings for this experiment. So just really setting the stage for how simple the system is to navigate, but more importantly, how much heavy lifting SML does for you and the group. So once we've completed that, we're done. We can publish this experiment, we can start talking about this, we can run new experiments thereafter, but that's how easy SML is. Regardless of your knowledge of machine learning, you can go in and get as much help as possible.